Okay, having discussed horizontal oscillations of a spring mass system, time now to look at vertical oscillations. So let us say we have a rigid support like this and we have a spring hanging from this fixed support. Let us say the length of the spring. This length of the spring is, say, capital L, and let us say this particular spring is of length L and the spring constant is, let us say, K. And now let us say I attach a weight mg or mass m over here. So I'll have a situation like this. When I attach a mass over here, there will be a small elongation in the spring. So this is the mass m attached over here, and there's a small elongation in the spring. Let us say this elongation, this much elongation, let us say is small l, just by attaching the weight over here. Now, if you look at the spring mass system, it is in equilibrium, and therefore all the forces acting on this will cancel out each other. Which are the two forces which come into play? One is the force F, the restoring force because of the elongation of the spring, and mg, the weight acting in the downward direction. So, if I look at the equilibrium forces, I will get F is equal to, or I can simply write F plus mg is equal to 0. Let me rewrite this over here. F plus mg is equal to 0. The net force, the addition of these forces will be equal to 0. We know F is equal to minus kx plus mg is equal to 0. Therefore, kx is equal to mg. So this is the first thing that we done. And now let us say we apply a force onto this mass, maybe in the downward direction, and then release it. The moment we do that, the mass will start oscillating up and down. And now our objective is to see whether the oscillations are simple harmonic in nature. So what will happen is when I'm applying a force in the downward direction, there will be an elongation. So maybe at a given point in time, the spring will elongate further. Maybe it will be in this position. This is mass m. So the elongation is, let us say, since it is a vertical elongation, I'll call it y. This elongation is y. So it was in equilibrium position. I applied a force on it. It started oscillating at any instant, at any given point in time. Let us say the oscillation is, the elongation is y, and at that point in it is accelerating by, say, alpha. Now if I look again at the forces that come into play, the forces that come into play are F, the restoring force. I'll call this F dash. I'll differentiate because I want to differentiate from this force. And so the F dash is the restoring force acting in the upward direction, and mg acting in the downward direction. So F dash will be equal to minus k into, in this case now it will be y plus L, because this particular force takes care of both this elongation as well as this elongation. It causes elongation y as well as elongation L. So minus k y plus L. So this will give me minus ky plus, rather, minus kl. And if I find out the total force acting on the system, the total force acting on the system will be total force acting on the spring mass system, or if I focus my attention on the mass, is equal to F dash plus mg, like this in this case, F dash plus mg, that is the total force. Of course, in this case it is not equal to 0 because the spring is oscillating, it is not in equilibrium. So the total force is F dash plus mg. So what is F dash? F dash is minus ky minus kl plus mg is equal to, kx is equal to mg. Brother, I think I wrote here x, this should be kl, because we're not having x over here, we're having l over here. So this will be l. So kl is equal to mg. So minus ky minus kl is mg plus mg is equal to minus ky. So the total force F total acting on the mass or the mass spring system is equal to minus ky, where y is the displacement. And we know that force acting on this mass is mass into its acceleration is equal to minus ky, and therefore we can say that alpha is proportional to minus y. Or before that, I may put it like this. I may put this equation as alpha is equal to minus k upon my. and from this I can say alpha is proportional to y. And now you very well know this condition, that when the acceleration is proportional to displacement and is in the direction opposite to displacement, the oscillations are simple harmonic motion. So this again shows that the oscillations of the vertical oscillations of the spring mass system are simple harmonic in nature, because alpha is proportional to minus y. Talking about the time period, t is equal to 2 pi displacement upon acceleration. The standard equation for time period of simple harmonic motion is equal to 2 pi. Displacement in this case is y, acceleration is alpha, is equal to 2 pi y upon alpha. Now, if I look at this equation, what is y upon alpha? Is equal to m upon k. Y upon alpha is upon k. I'll ignore the minus sign because time is a scalar quantity, so y upon alpha is equal to m upon k. And from this we can see that the equation for time period of vertical oscillations is same as the one that we got for horizontal oscillations. Right, so that's what we have shown over here. We have shown one thing, that this is simple harmonic oscillations, and also we have found out that the time period is same. A final point is that if I take the value of k from over here, right, so if I take the value of k from here, k is equal to mg by L. So if I rewrite this equation, is equal to t is equal to 2 pi m by k. K is equal to mg by L, so mg is equal to 2 pi square root L by G. And this equation, t is equal to 2 pi square root of L by G, looks very similar to the equation that we had for simple pendulum. Right? In simple pendulum, this L represents the effective length of the simple pendulum, whereas here L represents the elongation of the spring when mass m is attached. So if I know the elongation in the spring L, I can find out the time period of the simple pendulum, the time period of a given spring by using vertical oscillations. And the point that we need to discuss further, and that's a point that you need to think about, is that what would happen if a mass m is attached to two springs. Let us say we have two springs attached in parallel and there's one mass. What kind of equation will we get for time period, or whether it will be a simple harmonic motion or not? That would be the topic of discussion in the next video on vertical oscillations. Thank you.